but since the 1980s, they've really gone from a centralized power plant infrastructure to lots and lots of these combined heat and power systems that are distributed all across the network at the low to medium voltage level. And that's exactly what's happening with, you look at distributed energy, what's going to occur on the grid, where you're going to have lots and lots of distributed devices that are now hooked up. They're going to be putting power back on the grid, back feeding. So it's going to be a different future. Millions, tens of millions of these devices could be connected to the grid. The complexities are now at the edge, where you have demand response, distributed energy, microgrid. This concept of grid divorce is an interesting one. It's people who are actually designing new developments where they don't actually need the grid anymore. They produce a positive net export, and so the idea is, does it really become a support system for the grid, or does it cut itself off completely? Those are more futuristic scenarios, but that's a potential reality. And as Dave talked about, one of the principal causes of this large outage that happened on the East Coast, 2003, there was another one a while back where the whole western interconnection went out, is this lack of situational awareness, and where there was sensors and there was relays that had values that tripped that may not have been context aware. I mean, they may have been values that were appropriate 10 or 15 years ago, but they really could have anticipated that the problem wasn't as bad as it was, and instead of the whole system shutting down, it could have survived various components of the system, and so made a much smoother, graceful outage. And that's kind of what I think a lot of the larger scale smart grid DOE efforts are about, is really how you survive the system. And so this really suggests that you really need to have a distributed intelligence aspect in the controls. And I won't talk about the embedded intelligence software, again, as one of the building blocks. So in the example of distributed solar, distributed renewables, and I would say I'm going to focus on PV, on solar. Right now, if you talk to distribution engineers, it's really just it's noise on their system. It really doesn't show up on the radar. But there's a lot of talk and a lot of increasing numbers of PV systems that are going on to feeders. And I'm going to talk about one particularly in Marin County, and I'll tell you about the numbers. But when you start doing that, you start there's lots of issues related to too much backfeed on the system, which can destabilize the network. And so it's not a situation of the grid would love to have the power backfed back on, but it's not designed for that. And that's one of the issues from a control standpoint, as well as the cybersecurity. So it's really it's the voltage, it's the instability of that when it goes back onto the network that's really a big issue with distributed PV. If you look at the DOE study, this was based on investment tax credits getting extended, which already happened to 2016. There's been companies like Solar City and Sunrun and others who are actually leasing solar systems to residential customers in California. There's things like feed-in tariffs that are really driving a lot more PV than people imagine. And I think the numbers are something like 10 to, I think DOE predicted 26 gigawatts of solar PV by 2015. I've talked to Dan Kahn at DOE, and I think these numbers are actually maybe conservative. So there really is going to be a rapid acceleration of the number of these PV systems that are going to be connected to the grid, and it's something to consider. So if you think about what happens is you have voltage regulation problems with photovoltaics and solar on the system. A lot of times, a lot of distribution systems are designed for, as soon as you reach something like 10% of a network's capability, then the system can't handle it. I know, in fact, the PG&E system is designed where at 10% they want to be notified, and they actually want to know how that power is going to be routed back on their system, because it can actually destabilize, but it can open switches, and that destabilizes the rest of the network. So, and also when you think about microgrids, and you think about microgrids with solar, what you really want a microgrid to do is to be able to do an intentional island, be able to island the system and have that all the power generation inside the microgrid actually providing power to the customer. The way they're currently limited through IEEE 1547 interconnection is that when when if there's a loss of voltage or there's some kind of a fault, the systems actually shut themselves down for safety of the network. And so we're working on all those issues around what to do about microgrids, but that's a significant disadvantage right now of the system, is that when the system goes down, all the distributed systems go down as well. Unless you have a dedicated circuit and you have a backup generator in a building, that could be a different scenario. So large-scale renewables at the feeder, we're working on a project in Marin County. It's been a 3-year project, and they currently have about 8 megawatts of solar in on their feeders, and they anticipate they can do up to 200 megawatts on about 250 megawatts of peak capacity. So they can do a fairly high penetration of PV. They're moving very, very aggressively towards those goals. So we're demonstrating, we're actually doing a press release ribbon cutting this Friday with Marin County and Department of Energy who funded it, and looking at 5 or 6 facilities with PV and how that integrates, how you take that information and how you provide it to the utility at the distribution level. So instead of it just being solar that shows up on someone's radar on a website, this is actually going to be integrated into the distribution system, into the feeder. And there's a lot of issues that we're working on there. But again, most of them start with, most of these issues about getting to this intelligent agent with semi-autonomous control starts with just understanding what's going on with the system. And you have a decision support system that allows operators to understand what's happening, and they can be told all the priority levels and all the cost structures. And then, over time, you can start getting to automation, but that's a long way off. This is another diagram just showing what we're doing in phase 2 of this project, which is we're really integrating demand response, storage, and PV, and integrating all that into the California ISO demand response programs, into the utility distribution centers and things like that. So for the long-term basis, this is what solar is really going to be integrated with a whole bunch of other technologies. It's not going to be standalone. And that's where when you start thinking about putting strategic storage on the network, and when you start thinking about doing intelligent demand control together, you really need to integrate those 3 things together. It's very much an integrated system. I won't talk about interoperability because there's plenty of conferences that talk about this, but this is a very large issue about thinking about, at the microgrid level, taking all the meter data and all the data from their Google power systems and all the home area network data and integrating that now into the distribution level. And that's a very significant effort. All that's now been turned over to the NIST standards. The Gridwise Architecture Council worked on this for 4 or 5 years and decided that really needed to push this towards a standards body. So they're really managing most of that capability now. This is a diagram which is sort of the 3G system of the future, where you talk about embedded intelligence, technologies, sense and respond, various types of technologies that can go on an actual distribution feeder, and advanced networking, where you have different types of devices. You have gateways, and you've got actual smart devices, and you've got generation devices, and all this now has to be kind of coordinated. And where we're